yeah, anyway, let's start with Increasing Incident XRF and XRR. So basically, this talk is a little bit sort of summary, also overview of the stuff we did or I did in my about 15 years now, which I work on this topic. So basically, I give a short introduction. So what is the basic idea of this combined analysis, which was also termed Tracing Incident X-ray analysis by De Boer and van den Hogenhof. Then I will look a little bit in the samples, so what are suitable samples, or what samples we typically analyze, and also what information we can obtain about the samples. And instrumentation, of course, we have also some sort of traditional, so basically we're building our own instruments for this analysis. So I will go a little bit into detail there. And then last part is the actual evaluation, so software for evaluation, and also some examples, so some published results and also some recent stuff we are working currently on. So first, yeah, about the relation basically between TXRF. I think I will not go into too much detail about TXRF and XRF because, I mean, I assume as we are in the journal club about TXRF that most of you will be familiar with TXRF. So basically it's using this total external reflection effect on smooth surfaces. And typically for TXRF, we just measure at one angle. And we assume maybe that we have, if we have some sort of chemical analysis, then it's just a droplet or whatever, which is right on the surface. So it will form sort of a residue on the quartz reflector or silicon wafer, whatever you have as a substrate or sample area, basically. And here we can just use basically this double excitation effect typically, so that we measure at a point and have low background as the intensity of the fluorescent signal from the bulk material is quite reduced here in this angle range. And of course, then we have double by incoming and reflected beam. Basically, it's just a sum over the incoming and reflected field. Because we do not see interferences if these particles are relatively large compared to the field effects. So in this case, yeah, we'll just measure one point typically, so just one angle, which is maybe in commercial instrument defined by the manufacturer or whatever. So in Tracing Incident XRF, but we are using actually that this curve shape or this angle-dependent curve shape changes depending on which type of sample you have. So as I said, if we have the substrate, which is more or less the part, and we have a curve shape like this, so we can clearly see, okay, it's total reflecting in this area and below the critical angle. And if we go above the critical angle, we start to penetrate deeper and deeper into the substrate. And then, of course, as I said, for residues, it's basically this double excitation below the critical and then above. We should have approximately one, also just a normal intensity, because we are no longer reflecting on the surface. And for very thin surface layers, we expect something like this curve, which theoretically even goes up to 4 times the excitation if it's very, very, very thin. And this is caused actually by the interference of these two fields of the incoming and reflected beam. And the same basically is also true. So in this case, it's maybe layers and film, but we can also use this effect for excitation of an implant in the surface, for example, or also to get higher intensity and detection limits and so on for contaminations on the surface, maybe. The one thing I want also to mention now is that one thing that is can be problematic actually is for if we do TXRF analysis of particles, where small particles, nanoparticles, then the curve shape will no longer be this step-like curve, but it can be also something different depending on the size of the particles. So if we have very small particles, actually, it can be that it's no longer this step-like curve, but really some defined maximum somewhere. And then depending on the distribution also from internal standard and at which angle we are measuring, maybe the quantification can be wrong. So that's something also, maybe if you're just doing chemical analysis of nanoparticles, you should keep in mind that with nanoparticles, it can be sometimes difficult. Actually, we are using, as we'll then discuss maybe later, also this effect to try to determine size, of course, of nanoparticles, but it can be also an unwanted effect, actually. So yeah, basically now to come back also to the combined analysis, which is sort of the topic here. So we have not only the decreasing incident XRF, but also the X-ray reflectivity. And what this means, basically, we have then this incoming beam, so which is in a small angle range totally reflected, but also above the critical angle, it's still reflected a little bit and can be measured. And maybe some of you will be familiar with this. I mean, it's relatively common also for thin layer analysis and so on to use X-ray reflectivity measurement. So basically, you put on a second detector. So we have not only this fluorescence detector, but also a detector for the reflected beam here. This can be just intensity based, so maybe some as an only non-energy dispersive detector, but when we are also using silicon drift detectors for this purpose, depends on the actual setup. And basically, as I mentioned before, this was called actually from Van den Hogenhof and before they called it Gans incident X-ray analysis. So this combination of these two different techniques, sort of, which come from a little bit different background historically, and that's sort of a little bit a shame that I think that it's still not sort of established to use this more often, because the X-ray reflectivity is very good to giving electron density, but we have just a reflected beam, so we have no specific information about contaminations or composition of the sample, which is clearly visible, of course, in the fluorescence, where we get the characteristic lines of these elements in the sample, so we can directly see more or less what is in the sample, of course, up to a certain detection limit. But anyway, we can distinguish different compositions more easily than with XR alone, where maybe some difference in composition will not be visible because the electron density is so similar. So, and yeah, I sort of see it also as two sides of the same coin in this case, because I mean, it's just two informations which are contained, or different, also complementary information sometimes, which are contained in this different detected signals, sort of. So to summarize also a little bit before we go to the samples, what can we actually do with it? So first of all, I also mentioned, I think in the title, it's basically it's non-destructive. If we have a wafer sample, we can analyze it with the X-ray beam, and it will take no damage. I mean, of course, there are some limits. If you give it to a high intensity underliter beam, it can be maybe a little bit more problematic, but typically in the lab, with X-ray tubes, there will be no problem of damaging your sample. Then one advantage is also that it works for crystalline and amorphous materials. So for XRD, for example, just working if you have crystalline samples, so amorphous are basically transparent, sort of. But we can, of course, analyze both. Then the XR information we can directly see, as I will show later, then a little bit, is actually the thickness, density, mainly on the surface, but also of deeper layers. And then, of course, the electron density contrast of different layers and also the roughness. And of course, XRF can then add some information about elemental composition and also provide some limited, maybe elemental depth profiling information. So now let's go to the sample. So typically, I mean, that's a little bit maybe also historically, of course, we can here I've shown the wafers, which are quite common, or which were quite common when I started to analyze wafers and so on, and of course layers on wafers. But of course, it can be also other stuff like silicon quartz reflectors or whatever. Anyway, the main point is that the surface should be flat and that will homogeneous. So basically, it should have a surface roughness well below 3 nanometers, which is of course given for this industrial wafers, which have roughness which is even below 1 nanometer sometimes. And for analysis of layer thickness, actually, surprisingly, I mean, similar maybe sometimes like in TXRF, that less is better. So layer thicknesses in the range of maybe some nanometers to 20, 30 nanometers, or even 50, or maybe optimal, whereas then we are already struggling with layers about 100 or 200 nanometers in thickness. And I think it's sort of, I mean, in TXRF, if you think about it, it's quite similar. I mean, the more sampled mass you deposit, the more complicated you get with absorption effects and so on. And for us, for the layers, it's actually the problem that if we have thicker layers, then we will no longer see in the reflectivity, but also in the coincidence, this interference effect that well. So depending on energy, of course, you can change it, as I will also maybe show you a little bit later about this can basically play a little bit with the energy of the incident beam or to get maybe better contrast for this thicker layers. But anyway, I'm quite happy if I have layers below 50 nanometers sort of. Yeah, and then one topic which is also sometimes, because we have historically also made some comparisons with SIMS and so on, and they have typically quite small samples, maybe some below 10 millimeters, which is quite problematic for us actually, because the incident beam, of course, spreads over a very large area at small angles. So, and we want to excite the sample as homogeneous as possible. So it's very good if you have at least 20 millimeters size. I mean, for quartz reflectors, it's of course typically no problem. Also for wafer pieces, we have them typically larger. But as I said, if we do some multi-technique analysis, it can be sometimes problematic because other techniques might require smaller samples. So yeah, sometimes this was difficult. For XR, it's a little bit more forgiving. There you can really use also knife edges, small angles to limit the beam footprint, and cannot get away maybe as small as maybe 5 millimeters or so. But then, of course, we have the problem that we can no longer measure our tracing incident XRF because the knife edge is actually in the center of the sample where the fluorescence detector should be. Yeah, and for layers, of course, it's advantage if you have high contrast and electron density, but yeah, it depends. And of course, if you have this fluorescence information additionally, then this can also be helpful to alleviate this problem a little bit. So, what can we directly see if we look at the analysis, maybe on some measurement? So in this case, it's just simulation to make it more easy for me. But anyway, it's quite realistic that if we have some different densities, of course. For in this case, I just took some gold, nickel, silicon, or plexiglass PMMA. You can see that they are quite different densities, and of course, you can see directly that the critical angle shifts. And this is actually also maybe the first information if you have just a substrate, or also if you have a relatively thick layer. And we can already see from the critical angle, so basically where the total reflection starts to drop or no longer be valid. But there we can see, okay, here the density shifts because of this the critical angle shifts because of the density. And of course, as if you see here, we can also, if we see the description of some simplification actually about the calculation of the critical angle, and it's not only the density, so the rho here, which is relevant, but also the incident energy. So we have, if we have smaller energy, we have quite larger critical angles, which sometimes can also be helpful for the analysis. Okay. Yeah, then the next part of information you can relatively easily extract. So depending, of course, if you have one layer, it's quite easy. If some multi-layer structure, it can be more difficult. But typically with the XR, it's quite easy to see the thickness of the different layers. Basically, you could even do Fourier analysis about the maximum minimum, and so about the frequency basically of this intensity changes, and calculate the provided the different thicknesses in the sample. And basically it's called Kiesig fringes, these oscillations here about which are caused basically by the interference again of the incident and reflected beam. And as you can see here, the XR typically goes over several orders of magnitude, because here in the total reflected beam, you have basically the full primary beam, whereas then it drops significantly after the critical end. You can go down to, depending on the quality of the sample and also maybe of the instrument and so on, can go down to -7 or -8. Yeah, here this case it's just, for example, just some cobalt layer on silicon, but basically for the XR it doesn't make too much difference what kind of layer, what element it is. Basically it just shifts the critical angle depending on the density of the layer, and otherwise this distance between the maximum and minimum basically just depends on the energy of the incident beam and the thickness of the layer. Whereas for placing incident XRF, it's a little bit more complicated, as you can see here, whereas we can see here a direct relation basically between thickness and the distance of the maximum minimum. Here it's changing widely the shape of the curve. So that's basically also why, I mean, in XR it's quite similar. Typically for the evaluation, we calculate some simulations and compare it. But here it's, also even for some sort of, even for the evaluation, it's quite difficult to see what is happening, often if you have multiple layers. So there you have basically no other chance than calculate some simulations and compare to a measurement curve. And you can also see here nicely maybe that already for this 100 nanometer, this curve already looks quite similar to a substrate curve, so some bulk curve. So we can see that, as I said, basically 100 nanometer is already relatively thick for in XRF, actually. So again, to come back also to the nanoparticles, I mean, I've shown this before. Here it's quite nice. I mean, we can also use this standing wave effect, or this interference effect, to determine the particle sizes, or try to determine particle. Of course, there are some limitations. The particle should be spread out relatively homogeneous over the surface and shouldn't clump together and so on to make this work. But in the past, we already managed to do this with relatively simple preparation technique, actually. So now then the next part, which is often a question, is the roughness of some of the samples. So first we have to talk a little bit about what roughness actually means in this case. Yeah, here we can see some high resolution transmission electron picture. And you can see the silicon and silicon oxide are quite smooth here. Whereas then, of course, there starts to be some build-up of actually some waviness here at the surface. And that's maybe what some idealists example of what we typically assume. So basically we assume that there's some nanoscopic roughness, or roughness in the nanometer range, and with some sort of distribution. Commonly one assumes that it's sort of a Gaussian distribution of the distances basically from an assumed mean. And what we then describe as value basically for the roughness, more or less the root mean square roughness. And so the sigma is just the standard deviation of this Gaussian distribution. Interesting here is that basically with GIXRF and XR, we are basically measuring a relatively large area in square millimeters or even centimeters, I mean, depending on the incident beam and the angle. And basically averaging over a large area. So in this case, it's also almost indistinguishable between some sort of nanoscopic roughness or some actual grading of some interfaces. This is basically in the calculation, similar effect because we are just averaging over this jaggedness about this maximum and minimum pits and valleys. So basically in the calculation, it's quite similar to some grading effect. So, you know, that's also maybe a limitation, but otherwise it's relatively simple to measure the roughness of some layers, as we see here. So first, substrate is relatively clear, so that's why also we suggest also for the TXRF, typically the quartz reflectors should be smooth and polished, because as soon as we are hitting some maybe, yeah, even already at 1, it starts already dropping here, but I mean for TXRF it's not that dramatic typically, but for grazing for the XR it's relatively significant that already at 2 nanometers we're already losing much of the intensity of the reflected beam, and at 5 nanometer it's dropping quite dramatically here, as you can see. So basically it's, if the substrate is already that rough, then it's almost impossible to get any good information about the layers because all information about the reflected beam will be lost. For fluorescence, it's a little bit better in that sense, because as you can see here, maybe at 1-2 nanometers, it's not that much a difference. But of course, interesting, as you can see, if the reflectivity drops, of course, then the fluorescence will rise because we're penetrating deeper into the sample and causing more fluorescence in that sense. Of course, for excitement, it's just a simulation. So the problem is also that we have not only losing basically this information about the specular reflected beam, but actually also causing more absorption, more scattering, and so on. So also the background in the reflectivity detector will rise. So anyway, suggestion is if you want to do some measurements, typically just aim for roughness well below 2 to 3 nanometers. And if you look at the layers, then if you just take the substrate, which has good roughness, and deposit a layer, then the layer roughness will, of course, also influence the analysis results. As you can see here, if you have 0 roughness, which is, of course, hypothetically somewhat, then these interferences will basically go on to infinity. But in a realistic sample, maybe below 1 or some nanometer, then we have still a relatively large angular range where we could have good interferences, so we can base our analysis on many maxima and minima. And of course, the more maxima and minima we have, better. And as you can see, for 3 nanometers already, it's quite problematic because basically we have just 1, maybe 1.5 sort of maxima. So this can be already challenging to analyze. And yeah, for fluorescence, it's, as I said, a little bit more forgiving. The curve shape changes a little bit depending on the roughness, but otherwise it's still clearly visible sort of what's happening. Well, and why, I think maybe that's maybe a little bit constructed example, but anyway, we have also some other samples. So this is, for example, if you take this copper, pure copper, and compare it with this copper alloy, which also contains nickel and iron, those two, so basically it's pure copper and also this alloy have very similar density, so it's basically the same density and also similar electron density. So in XR, they look the same. But that's my reason also to say just take also the fluorescence signal, and you can see immediately if there's some in this sense for typical layers, maybe you know what you're depositing, but it can also happen, of course, that there's some unwanted contamination or whatever. And in the fluorescence, we typically clearly see it, even if it's just in the percentage or even the ppm range. Ppm is maybe a little bit. ppm range you should typically see in the fluorescence signal that there's some contamination. So this can be helpful also to trace maybe some contaminations. Yeah, exactly. One sample we just had recently, maybe if you have also some hafnium silicon oxide or something like that, and just wonder how much silicon is in your hafnium silicon oxide. If it's basically the composition you want, then you can also look at the different concentrations there with the fluorescence, which is quite helpful. So then let's go on to the instrumentation. So that's also, I mean, a little bit from my side looking back, basically, because that was basically where I started with my master's thesis. Was basically also working during the ANA project on this grazing insect XRF chamber, which was basically at this time a modification of our existing, or sort of partly existing, vacuum GIXRF chamber for grazing insect XRF measurements. And I mean, it's just the basic components. You have just X-ray tube, multi-layer, and fluorescence detector here. With the sample stage, we can be rotated. And what we added later also here is then a second STT to measure the reflectivity signal. In this case, we can, as what I routinely do is basically change between different tubes. So anode materials, so basically molybdenum, copper are quite common in this case. Which gives, or which can be helpful, because of course for some samples, maybe if you have arsenic or hafnium or something like that in the sample, then maybe you want to have the molybdenum tube to excite the higher energy lines, whereas then for other samples where there are only elements or lighter elements, maybe lines, elements which have high lines in a good range. So for copper, maybe we can change this. Otherwise, yeah, but this may be interesting here that we also use an STT for the reflectivity detector and with a filter wheel, of course, to dampen down the intensity at the low angle range. Because as I said, there's basically several orders of magnitude to detect, and in the primary beam, the intensity is much too high even for an STT. So we have to use some absorbers to reduce the intensity at lower angles. Yeah, or maybe what I want just to mention, basically, we have a quite similar chamber also for detection of light elements, which is using a chromium tube, and STT with now with the silicon nitride window with a very thin, so just some 20 nanometer silicon nitride window. Yeah, so it's basically from the setup, it's quite similar. It's just that it's basically the monochromator is also in this vacuum chamber. I think that's also one of the strong points historically in the Domestot here, that we're trying to building also vacuum chambers. This can be helpful for detection of light elements, of course, because then we don't have to deal with the absorption of the fluorescence line in the air. But otherwise, it's also helpful also to reduce scattering and so on. But on the other hand, the vacuum is relatively rough, so it's about 1 millibar maybe in that range. So you don't have to deal with ultra high vacuum like for electron microscopy or something like that. Yeah, okay, so that was basically the first approach we choose for building a combined instrument. And the other approach, which is sort of also relatively clear, sort of, is that you can also take a diffractometer, which is already built more or less for X-ray reflectivity measurements. What it's missing is basically the fluorescence detector. So in this case, I mean, at the moment we already have some beta holder, but I just want to show the first tests or experiments were relatively simple. We just took the stand, mounted the STT above the sample, just in a well-defined distance, so about 3 millimeters, which we measured with some distance holders. And basically you're good to go from the instrumentation side. Of course, the more problematic side in this case was actually the software side, because we had to synchronize the detection of the fluorescence spectra with the acquisition of the reflectivity and the movement basically of the motors for the angles. But otherwise, it's relatively straightforward to set up and gives very good results. And what this also provides is, because here in this setup, we can relatively easily change the X-ray tube. but the monochromator is a little bit more difficult because it's actually mounted with some screws and relatively fixed. I can just change the incident angle with the tube to get the break angle for different anode materials for the different characteristic lines. But otherwise, the monochromator is fixed. Whereas for this instrument, it's relatively easy also to change the incident optics. And in our new design, sort of, we also tried to make it easier to change the incident optics. So this is a chamber we're currently building. So it's just put in here the schematics basically from the design, although we are already starting to build it here. Just easier maybe to see it here, this whole setup. And this is basically a cooperation with the University of Utrecht, which we're in now. And the idea here is again to have a chromium tube or chromium anode for the excitation of light elements, in this case actually down to carbon. And on the other hand, also maybe change to molybdenum for excitation of other elements. And in this case, of course, you have to change the tube, but here there's foreseen already that you can move basically between different mirrors. In this case, we are now using some parallel beam mirrors just to get a parallelized beam, and can maybe also, depending on upcoming developments, and so we're thinking about maybe also mounting a focusing mirror with relatively large focusing distance. So that's also why I decided to separate a little bit this optics chamber and the experimental sample chamber that we want. Just maybe it's also possible to change this relatively short tube to a longer tube so that we can also get longer focusing distances. And otherwise, it's typical sort of TXRF setup. So basically, it's just here that the monochromator is mounted, and here then you have the sample stage with the different position and options. You can rotate it, so tilt it, and whatever. And at the moment, yeah, it's at the moment just foreseen now just a budget limitation, sort of a screen, a beam monitor, so a screen with a camera, but in the future, it's also planned to mount a reflectivity detector here. So yeah, then, as I said, we can have different energies for the fluorescence. So that's helpful for the fluorescence, but on the other hand, it's also helpful for the reflectivity if you look at different energies. For example, here, if we have this, that's basically calculated for the same instrumental resolution, but for a relatively thick sample, like this 200 nanometer nickel on silicon, for example, then we can see that for the molybdenum, we have practically no longer any interferences visible. Whereas if I switch to the chromium energy, then we have clearly visible fringes, and also for copper, it's still quite easily visible. So that can be helpful also depending on the thickness of your layers, then maybe to go to lower energies, which are more, in this sense, more forgiving for the or provide better interference effects in this range. Of course, the problem is that in a typical diffractometer, which is just an open air space, basically, you have then much higher absorption. So chromium is, of course, much stronger absorbed in the air than the molybdenum, so basically losing somewhat on the intensity side. But of course, in this case, if I don't see any fringes, then even the high intensity of the molybdenum will not help me. Okay, so the other story which I investigated then, because we could relatively easy switch monochromators in this diffractometer, was to investigate a little bit also the effect or the influence of the different monochromators on the measured signal. So in this case, I just want to give maybe a little bit of an overview, because of course it's a trade-off. If we have a focusing, so some elliptical curved multi-layer mirror, basically, then we gain much more flux. so it's much higher intensity. But of course, we're losing also on the spectral purity, so this is lower. So basically, in this case, we have K alpha, so which is K alpha 1, K equal 2, maybe a little bit K beta contribution. And of course, also the beam divergence, especially in the focusing case, will be higher because it should be focused on one point, of course. So it's sort of, I mean, it's maybe not divergence, it's more convergence, but anyway, the angular resolution will suffer. On the other hand, then we can go to parabolic curved crystals or some collimating, which should produce an almost parallel beam, but of course, depending on the quality of the mirror, and also because the source is not infinitesimal small, so it's just some for tubes, it's some 14 micrometer size, maybe line focus. Then we have not perfect so zero beam there, but still some relatively smaller compared to the focusing mirror, and lose a little bit intensity compared to this spot already, have a little bit better divergence. And then there's an option also to have some hybrid monochromates, which basically combine some parabolic mirror to get more intensity, parallel intensity onto the crystal. And then in the second part here, you can see a little bit the schematic. So basically have some parallelizing mirror, so collimating mirror, which, and then a 2 pounds crystal, so which then sort of combines a little bit the advantages of crystals. So basically have almost pure K alpha 1 with a little bit K alpha 2 maybe, but basically no K beta contributions anymore. And then you have then, of course, better spectral purity, as I said, and the intensity will suffer a little bit, of course, again. And the divergence will increase in principle, well, as a increase in this, as a decrease actually. So it's better for our measurement because we get better parallelity of the beam, basically. And the last option, which actually I didn't test, was there's also option maybe to get some multi-pounds of, in this case, 4 pounds crystal monochromators for the diffractometers. But of course, they will have the best possible sort of spectral purity on this standard instruments, sort of. But of course, for fluorescence, it's a little bit problematic because the intensity will drop so much. And basically, what I did, I just compared a little bit on one sample with different optics, and that you can see here. For this is the hybrid monochromator, basically the best divergence, sort of smallest divergence. And here's for this focusing beam mirror, which is the largest, and you can see here already for the this is basically the fluorescence curves here. So for the silicon, in this case, it was with the nanometer nickel on silicon, and this caused this intensity, also this fringes basically, and also in the fluorescence signal, it's clearly visible that for this smallest divergence, best divergence optic, in this case, it's still here a step function, sort of here, but here it's basically gone almost, and also here you can see here a small peak actually, whereas here it's just dropping down. So, I mean, in this case, it's not that problem because it's just one layer, so we can still analyze it maybe with the highest intensity mirror, but for more complicated layer structures, it's quite helpful if you have some have maybe some better resolution option. Another instrumental effect, which I shortly mentioned before, actually, which sort of is also connected a little bit to the sample size for the reflectivity, mostly, is then the beam footprint. So in this case, I just did some simulations. So if you have a relatively large beam, and you can see here that already for some 10 centimeter samples, the curve will not look like what you expect from typical, because for XR curve, typically would assume a relatively straight hop where the total reflection is happening, and then a steep drop at the critical angle. But here maybe it's actually more rounded shape already, and here then if you got smaller samples, it's even more problematic. So basically, you have then to correct for this during the evaluation. And if you have a smaller beam, in this case, it's actually helpful a little bit, because here for the 100 millimeter sample, still have a quite more straight intensity profile here in this range. Whereas again, for smaller samples, it's also problematic. And this can be explained, of course, because I mean, at very small angles, we have a very large footprint, because it's basically dominated by the sign of the incident angle. And here we have a relatively large incident area on the surface of the sample, and the larger the angle becomes, the smaller this area will be. And this has also, of course, an influence on the fluorescence, detected fluorescence signal. Here, actually, it's so, because here you can assume maybe even a smaller beam would be helpful, maybe for smaller samples. But on the other hand, for the fluorescence, actually, a smaller beam requires more corrections, basically, to the intensity calculations. Because here, I mean, here we compared basically a measurement we did at the Atom Institute with our instrument, which had just some slits to reduce the beam profile down to 50 micrometers, also to limit the divergence, of course, but also to have a quite well-defined beam. Whereas at the latter, they have a larger beam. So this is actually the fluorescence beam, and maybe I should mention this measured with the vacuum chamber, which was basically provided by IEA there. So it's which is quite similar to this chamber, which is also at Soleil and at the BTB streamline at Vesey. Yeah. Anyway, it's a relatively large beam, and so we can see here for the electro, quite well. So this is basically a gold layer on silicon, and here we can see that the gold is actually what it's acting, because it's about 100 nanometer thick gold. But in this case, the gold and the high absorption are acting sort of a little bit like a substrate in this energy range. And we can see here for the electro measurements, the curve already looks quite recognizable as a substrate curve, sort of, as for our measurement here in the lab. It looks quite distorted because at the higher angles, basically, we're sort of losing intensity, and this can again be explained. We look at the beam profile or the beam footprint on the sample. As you can see here, basically it's just shrinking, and if the beam is too small, then we just lose intensity. Also lose sort of the theoretical calculation without any corrections. Okay, so that brings you now to the final part, which is just some words about the evaluation part and also some examples. So again, if we go back, think about how we can evaluate or calculate this, basically the intensities. One of the maybe important parts is here actually is the critical, the effective index, and which is then connected, of course, to the critical angle also by the delta here. So basically, in the X-ray regime, we can describe the effective index like this complex value. So this is the delta is the dispersion part, and beta is the absorption part, and this has also some influence on the calculation, because we can derive these values actually from the atomic scattering factor. So basically, it's based also on the electron density sort of the atoms in the sample. And this is quite nice to make this calculation sort of self-contained, and also basically the same formalism for reflectivity and fluorescence. And here you can also, maybe I want to point out this interesting effect actually also physically, that vacuum air is actually optically denser than our materials in the X-ray regime. So that's why we actually have this total external reflection. Okay. And for the calculation, then it's also interesting to look at what's happening on the surface of the sample. Basically, we have this interference, so between the incoming and reflected beam. And you can see here at the critical angle, actually we have this maximum here, sort of in so actually the maximum area in the surface of the substrate, sort of. Whereas in other angles, at smaller angles, it's shifting out of the surface. So that's explaining maybe why a surface layer just increases here in intensity at the critical angle. Otherwise, yeah, after the critical angle here, you can see that it's already dropping quite dramatically. So the sort of the interference breaks a little bit down. So this sort of gives us, because we can also move basically the distances of this maximum and minimum depending on the angle, but this gives us sort of a tunable roller in this nanometer regime. So for the calculation, just want to cover quickly, and it's just, it's relatively complicated. I mean, it's because basically you have to calculate, if you have a multi-layer samples and so on, you have to calculate for each layer, basically the transmission, reflected beam and so on. So first, of course, we have to calculate this reflective indices from the scattering factors, then calculate this reflection and transmissions. And the nice thing about XR, it's relatively easy. Here you're basically already done if you have this reflected and transmitted fields, because this is just the XR part, is just basically the reflected field, more or less. Whereas for the fluorescence, it's a little bit more complicated. So you have to also calculate the energy flux in the layers, and then calculate the fluorescence from this and so on. And then also, of course, the absorption of this emitted radiation. Yeah. And yeah, exactly. And for the evaluation, basically do this calculation, just then optimize the parameters to fit our measurement the best we can. So for this, of course, this was basically my PhD thesis, was writing a software to simplify this, and its idea was to make it as accessible basically as possible, so with some graphical user interface and integrated database, and also these different corrections for the setup effect. And if you want to use it, then just write me an email and I can talk about it. I can provide it. I mean, there's already some people using it. What sort of a spin-off a little bit of the software was also nice, that I could provide basically a website where also some tools and this different pages, basically penetration depth calculation with a sample helpful also for tracing inside XR, for example. Then we have effective index calculation, of course, the database with the scattering factors, and also maybe some simple calculation for one layer or two layer structures. So in this case, it's not included the full setup corrections, but just to give you an idea maybe what this looks like. So this I come to the examples. I just want to show you quickly. So first, this was a little bit was a starting point. Basically, this was some analysis of some relatively simple titanium layer at first we saw, but of course titanium is a little bit problematic because it's quite quickly oxidized, and in this case you can see that sort of a gradient of this oxidation, and just in this case it was the 3-layer model I used for the analysis, which fit the measurements quite well. So maybe one of the also technologically very interesting samples were from our cooperation with Leti and Wein. So basically they investigated here some transparent and conductive oxide layers, which contained, here in this case it was indium oxide, and then some silver layers in between. And the interesting part in this case, what's happening during the annealing of these layers. And so first we measured them here in Vienna with our copper tube in this case. As you can see, the course fits look relatively well. So this was just at the moment just as deposited sample, so without annealing. But the problem here with had a little bit uncertainty because there was some overlaps, of course, between indium L and silver L lines. So in this case, we then also went to the synchrotron, and we used basically the XR measurement. And we measured here in Vienna because there were better quality and also easier to evaluate because the energy we used there was relatively high, so it was 26.4 keV. So just to excite basically the silver line and below the indium edge. And you can see here, okay, we fitted on the actually I talk over here, but in this case it was mainly Béranger did the evaluation with my software. So basically it's just the fitting of this GIXRF measured silver K line and the reflectivity curve we measured here in Vienna with the copper tube. And in this case then the best fit was actually with not with the pure layers sort of, and also with some transition layers in between. So it looks like there is some, due to the annealing, probably some interdiffusion sort of the indium oxide and the silver. Yeah, and a step further was then the next part sort of this cooperation with data was then the investigation of some indium-free TCOs. In this case, it was some zinc oxide, which was doped with gallium. And again, here was the question: how does the annealing basically influence the sample? In this case, it was actually that the annealing was sort of helpful because, as you can see, it's sort of redistributed also, because in this first case without annealing we had to use a sort of two-layer model to explain the measurement, and then after annealing it was a little bit more confined in one layer sort of. So this was basically just sort of also study if it's possible basically to evaluate this or use this basically for the characterization of this type of samples. And of course, the results are also validated in this case with MS. But yeah, again, the advantage here, or the question was basically you can use tracing inside GIXRF and XR just non-destructive, because here, of course, if you use this plasma profiling, then your sample will be somewhat harmed. So in this case, it's easier or helpful also to have some non-destructive techniques. We can maybe also use of some samples in the production line, for example. So that was one example, which is one of the first problems I also came on when I started basically my master's, building this chamber and then analysis basically of this arsenic implantation in silicon, so characterization of arsenic implantation in silicon, and how to evaluate this. I mean, in principle, it's the same approach as I've shown you before with the layers. So in this case, we just discretized and the implantation profile and calculate our model from this. And this was actually this large ANA project where we compared different techniques. Of course, from basing inside GIXRF, it's also relatively simple to get the dose information. And as you can see here, and it's, depending on the techniques, there are some variations. Interesting, we also used actually the reactor here at the Atom Institute for some neutron activation analysis, and they are more or less in the same range. And in this case, we also noticed actually one problem. If we just use tracing inside GIXRF for the implantation, then it's quite problematic, because we have this sort of ambiguity between the different profiles. So basically, I could fit the same tracing inside GIXRF curve with this profile, so with this red sort of Gaussian shaped a little bit, and otherwise also with this almost just one layer thickness sample basically. But of course, in the XR they will look different. So this was actually one indication why it's really helpful in this case also to use the XR information. And this then we did a little bit later, just combine these two different informations. And then what you can see here maybe from the XR, that it's not clear, so it's not a very well-defined layer, but it's just some sort of change, of course, in the electron density due to the arsenic implantation, but still it's noticeable and can be used for the fit. And in this case, the final results look quite similar again to the Sims profiles, maybe just some variation, maybe 1.5 nanometer range about the depth, but then there's also a little bit the question how you define basically the surface in this case. So okay, and then the next, for me also interesting actually investigation was some organic layers, so for the organic light emitting diodes, because at first I was not sure if this will actually work, but it turned out that actually these organic layers are also very well defined. And in this case, the question was about some differences in the basically the position of this layer. So there's also some differences in solution-based deposition and vapor deposition in the performance of these diodes. And the question was, what is happening? Why is one better than the other? In this case, of course, and in this case, the main topic of investigation was just sort of 3-layer stack with the host layer here, it's called host layer. It's just basically some sulfur-containing organic layer, basically. And this was then differently prepared. So one vapor deposition, one solution processed, and then we did the analysis. And then I think as the XR itself is, in this case, helpful a little bit because you can see thicknesses of the different layers and so on, the structure. But it's not very sensitive, or actually not sensitive to the sulfur content because it's just about 1%. This has, in this case, no significant influence on the electron contrast. So in this case, again, the fluorescence was quite helpful because we could selectively detect the sulfur also. And then we realized that the best fitting model was also then if we also have some sulfur further down below in this HDL and buffer layers for the solution processed layers, for the solution processed host layers. So it looks like there was some diffusion going on. And another, so also what we did in relation to, so this was actually published some 4 years ago. But what actually we didn't got, but I want also to show because we just continued a little bit on this. Also, there was some fluorine, some organic layers, basically also for OLEDs with fluorine. And this we could measure in our low C chamber with chromium excitation. And this segment is also relatively nice fitting here. So that shows that also this, for these low C elements, it's possible to do this GIXRF analysis. Another, and also already a little bit older sample, but it's also interesting that I want to show you here because it also shows nicely that this is actually with relatively easy preparation and too much effort. You can also do analysis of nanoparticles in the lab. So here you can see some SEM images. So they're basically the same particles, just with different concentration, more or less. And in the range, according to the SEM, some 8 to 9 nanometers, and here we did just some measurement in the Gaussian GIXRF chamber with copper anode. And in this case, we deposited actually on a gold layer just to extend the angular range a little bit. I think that's similar, a little bit an idea to what maybe Manoj Tiwari showed you with this multi-layer. So deposition on multi-layers. In this case, we just used, just because it's maybe easier, cheaper, and so on, just to use a gold layer on a wafer, which you can readily buy, basically, and just deposit these particles on these gold layers. And you can see here, also this fits. I mean, it's a little bit discrepancies sometimes, but maybe that's also because it's, of course, this calculation is just for one particle size. And of course, they are not monodispersed, so there may be some size differences, and also maybe this agglomeration will maybe not also somehow influence the standing wave field. But in this case, even for this higher concentration sample, the fits still look quite nice, actually. And of course, yeah, that's maybe the point that the particle size, but we had the best fitting curves actually in the same range like the SEM, which was sort of encouraging in this respect. And then brings me to our actual newest development, why we're also actually building this new low-C TXRF chamber. Is actually analysis of carbon. And in this case, it's interesting, maybe we just tried for testing basically also some angle curves of plexiglass or PMMA. And this was acquired actually in our already existing low-C chamber here with a new detector with silicon nitride window. And yeah, of course, you can see in this plexiglass, this is the carbon peak, here, this green one, and this is the oxygen peak. They're quite nicely visible in this case. And then we can plot also and fit the angle curves. And well, as expected, I mean, at least it was a confirmation that the basic measurement works, is that carbon and oxygen curves behave like expected. In this case, for this basically pure carbon and oxygen reflector. But where we had actually a little bit of problem, which is maybe also what you want to mention maybe here in the end, like at carbon, it looks like it's a little bit complicated because it looks like it's sort of everywhere. So because we wanted actually to investigate some carbon nanoparticles, then we realized that we have also some carbon background actually from the reflector. So we just looked at some other samples. In this case, for example, just a 100 nanometer nickel layer on some thermal grown silicon oxide. And here we also have carbon unexpectedly somewhat. And also what's even more unexpected, it looks like it's going deeper than just the surface. I mean, basically, we can assume that there will be carbon on the surface, and not just from the air contamination, but it looks like it's actually deeper into the layer, even in the silicon oxide, whereas the oxygen fit behaves more or less like expected. And basically, that's sort of this indication here of this here, if you want, because I mean, basically on the surface, it's maybe a little bit oxygen, but then as soon as the beam basically hits the silicon oxide fully, then we get the steep increase. Yeah, so that's at the moment, like I would say, our topic we are working on is basically this carbon contamination, or maybe also how to get rid of this, or get maybe as carbon-free reflectors as possible to get good detection limits. And this is finally the conclusion of my talk. So I mean, I hope I showed you some of the combination of XR and GIXRF provides more information for the characterization and actually non-destructive characterization of layers, implants, nanoparticles, and so on. And from our point of view, it's relatively easy to adapt actually diffractometers also for GIXRF for some combined analysis. Yeah, for the analysis, I use my GIXRF software, and if you have further questions or whatever, then either contact me or you can also look at the website here. And yeah, thank you for your attention.
Yeah, thank you.
I just saw it. I don't know if there's a time limit. It's already about 1 hour. I don't know. It was not too exhausting.
No problem. I think it was very kurzweilig. So yeah, very impressive, especially the fluorine measurements. I thought that was kind of yeah, that this instrument can do this. Yeah, are there questions? Everything totally clear. Yeah, maybe I have a question for the contamination of carbon. So we usually never think of carbon. At least here we do not have these low Z options. do you think you have contamination also from your vacuum pump system, or is there no?
No, actually, this was also one of our first concerns. That's why we got rid of all oil pumps and so on. Basically, it's just now one membrane pump, which should be all free. So we tried to, and basically we don't need that good vacuum. So basically it's just about 1 millibar. So just this basic membrane pumps are sufficient. So we try to remove everything basically with code. So that's why also we have now a detector with silicon nitride window instead of the typical polymer windows, which are of course carbon containing, because we wanted to get rid of everything containing carbon, but still the effect stays the same. And up to now, yeah, it's a little bit, of course, we never looked, that closely at the problem. And so at the moment, it almost looks like it's really in the surface somehow in the sample. I don't know if anyone else has some experience. We're also trying, of course, now to talk with colleagues who are using XPS or Roger or something like that. But the problem is that we are actually looking deeper into this because, the information depth for carbon fluorescence is about 1 or 2 micrometers. Whereas the electrons are, of course, very surface sensitive, only the surface basically, so some nanometers maybe or 10, 20. And so, I don't know, yeah, if someone has an idea, maybe, what we also tried, maybe what I should mention, I think one of our students also started to try some plasma etching of the surface and so on, and then measure directly afterwards, and it looks like it improved it a little bit, but we see that's still very preliminary, I would say.
Yeah, I don't know. I have no idea right now.
No, it's probably a very specific problem. Yeah.
Other questions? Then maybe I have another question. So I thought it was very impressive, the data that you showed on the different layers. I think it was with the silver and was this indium oxide.
Indium oxide, yeah.
Yeah. So how small are these, or how small can these layers be to be distinguished as an individual layer? So what would you say? I remember seeing that some of those were like 5 nanometers.
Yeah.
Is that kind of a benchmark, or could it be even less?
It could be even less. In principle, I think if they're well distinguished, so basically one layer separated quite well from the next, it could be even 1 nanometer. So for the XR, it's a little bit problematic as the layers become thinner, then the angles become so large for the maximum, then maybe you just see 1 minimum or so and no second max as a minimum, then it's maybe becoming problematic. But 1, 2 nanometers, in principle, it could probably even do just single atom layers basically, but it's maybe a little bit for the fluorescence it should be visible, but for the XR it could be a little bit difficult, I would say. But 1, 2 nanometers, I think, are actually no problem. Basically, we also see sometimes from silicon oxide, so just native oxidation, basically, with just 1, 2 nanometers. You can see this actually also.
Mm-hmm. Okay, maybe last chance to ask a question.
Now I talked too long till everyone is tired.
Yeah. Okay, then I would say let's thank Dieter again for the very nice presentation and discussion.